Okay, in this video clip, I am going to show you how you start a consolidation test. Before you start the consolidation test, this is an incremental consolidation. What we're going to do first is we're going to find out or determine the machine deformation or the frame deformation. Some people call it also the compressibility of the system. Because when we apply the loads, which translate into stresses on our soil sample, not only the soil is going to deform, but the frame does deform. So what we're going to do, we're going to look at how much the frame deforms, and the software will automatically correct by subtracting the machine deformation from the soil deformation, so you get the net deformation of the soil. So in order to do that, instead of soil, we're going to use a metal disc. It's called a calibration disc. So we put the disc here. Okay, so you're going to simulate everything as if you're running a consolidation or soil sample. So you got the filter paper, one at the bottom. You got the soil, which is now a piece of metal, which is a calibration disc. You put the filter paper also compresses, and then you get this is the holding ring here, or centering ring, and then you have the top pour stone and loading pad. So you set up everything here as if you were going to run a consolidation test. Okay, what I just did here is I put my consolidation cell, I center it. There is actually rings here. To give you an idea, the rings are the typical size of soil: 1.4, 2 inch, 2.5, 2.8, and 4 inch. So you center it here, you get as close as possible to the load cell button, so you know that this is moving here. And everything is good to go here. The menu here, you can leave it anywhere except jog. Don't leave it in jog. So this is the menu here. What I did, I moved it slowly just to be close. So there is actually a gap between the steel ball and the load button here. If you have a piece of paper, you can see that you can slide in and out pretty easily. I'm actually going to fold this piece of paper in two, and I can see that I can go. So there is a gap here. Now, why I'm leaving the gap? Because the software automatically closes the gap for you automatically. So what we're going to do next now is everything is going to be controlled through the computer. All right. The next step, what we did here is we set up our consolidation cell with the calibration disk inside. So what we're going to do is we're going to load the software, and we're going to run the software to do the machine deformation. How often do you do machine deformation? Once. It's not going to change because the frame is not going to change. Unless you're changing something like a new cell or different size sample, 2.5 inch or something like that, that you might want to do it. But typically, you only do it once. And because you only have one frame now, then you have the file that corresponds to that has the machine deformation. So what I would do here is I'm going to go to the software that is called consolidation. I double click on it, and the software is loaded. That's the one we're going to be talking about tomorrow. Now when the software is loaded, it's blank. There's nothing there. what you need to do is you need to load the template file which created. The template file has all specific information to that particular load frame. What I mean by specific information is the calibration factors of the sensors connected to that frame, and also things like step multiplier, properties of the motor that is used. All this information does not change. You don't want to re-enter all the information every time. So what you do, you load the template file. You must load a template file before you run your test. So this is blank. I'm going to load a template file. I go to File and Load, and there's a template file that we created here for you. Now, once I load the file, it's going to give me some information that was in the template file that you need to update, such as the date, the sample information, the tester, the checker, things that change all the time. So you need to update that. Now, if you forget to update anything now, you can update it after the test or during the test. However, I do not recommend you do that, because once you start in a production mode for a big project like 50 tests and you forgot to update, it will become a mess. Steve is laughing about that. He probably knows something about it. So I am just going to update right now just to show you the date of the test, which is 03/25/2008. Okay, I am the tester and I'm my own checker too, all right? Nobody's checking my work right now. So I have that. Now, there's a logic here which I'm gonna go into the details tomorrow when I talk about the software interface. Now I'm gonna go a little faster than usual so I can do my machine deformation and get my test running. But tomorrow I'll concentrate more on very specific each step along the way and the logic behind it. So I have a specimen. Now my specimen diameter is the inside diameter of the ring, which I should have measured before putting it there. I'm assuming it's 2.875. So we have the initial diameter of 2.8. The height is 1 inch. We don't need to put the sample initial weight. That's irrelevant now, or the specific gravity or anything like that. What we're interested now here is doing the machine deformation. So I am going to jump directly to what's called calibrate machine. Now, this is, I'm going to put the stresses in TSF. Now, what I need to do is put the stresses that I am actually going to apply when I run my actual consolidation test. Where those stresses come from, the ASTM has a recommendation for that. So it starts with a 1/8 of a TSF, 0.25. Then you double the stress, 1, 2, 4, 8, 16, 32, and you unload it 8, 2, 0.5, and 0.125. So I have my stresses. I put my stresses there. What we call them target stress. So I put my sequence, load, and unload. Now, those are the stresses, just a target stress. When I run a test and the stresses are different, the software automatically interpolates between the lines, so you don't have to worry about that. You only do it once. So if I'm running a test and I'm running it at 0.2, 0.2 TSF, and here there is 0.1 and 0.25, then it will find the value in between, doing linear interpolation. So I have my stresses here. I go into view, system, make sure everything is okay here. One quick test which I'm going to be doing tomorrow and checking, I want to make sure that everything is working correctly. So I went to a system monitor just to check that there is a communication, the power is on, limit switches are off, and the sensors are alive and responding. One quick test I always tell people to do is the load. What I do here, I push on the load cell, and I should see about 20 pounds. That's what a normal human being who is not on steroids will push about 20 pounds. So that's a quick, easy test. All right, we're back to do our machine deformation. Something that was not recorded. We were checking the calibration, make sure that we're good to go. So what we did is we checked the load cell calibration and the displacement calibration. Those are very important because they're going to give us the correct results for the machine deformation, especially the load cell. So what we did, we took the load cell out of the frame, put it on the counter, and we put a non-dead weight, which was about 17 pounds, and we checked it. It was about 17 pounds. So that looks good. We checked the calibration. Now what we're going to do, we're going to go back to what is called the machine calibration that has a sequence of stresses that I have put in according to the STM standard and according to most probably the stresses that you're going to be using for doing your consolidation test. So what I will do, I'll go on the first step here, and I click on step. When I click on step, I get a prompt on the screen telling me position platen. Remember, we have a gap here, so position platen is going to move automatically and it closes the gap. So you always say yes, unless when you set it, you know exactly that is touching. So you do yes, and when you do yes, you're going to see that light on the motor up is going to go up, 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 and then when it touches about quarter pound, it will stop. So I'm going to click yes, and it's going to go up. And now it touched it, and then it went down. Now it's maintaining a very, very small load, so it's barely touching here. So now all the results are going to start right from zero, and it's maintaining that load. Now, just to show you that the feedback is coming from load cell, there's a feedback, there's what is called closed loop control. If I push down, I'm going to create negative pressure. If I push down, and the motor is going to respond, goes up. And if I push up, it's going to go down. Look at this. I'm going to push down on it. So it's trying to keep that contact constant, no matter what. Okay? And then it goes back to normal. So now automatically it made the contact. Now if I feel, yeah, it looks good, make sure it's all contact, I say yes. It's press OK when ready, cancel to board. So I'm going to press OK. Now what it's going to do is going to apply the first load. The first stress, first load to correspond to my target stress. I can close these, I don't need that. Now, I go, when it's quiet, I go to the next step. And I can check the graph. It only has 1 point here. And I do step when it's quiet. Now I got 2 points. I wait. This is metal, it's not consolidating, it's just applying and maintaining the load. So I give it a few seconds. Step. Now, because it's very, very stiff material, there's no give. So it will go up and down to this is not a soil. If I wanted to slow it down, I can. There is some controls here. It's called PID control. But there is no need to change things on. Just let it. It will stabilize by itself. How many times you do this? You do it a couple times just to make sure that everything is okay. There was no gaps or things. So everything is all seated together. So now my calibration is done for my load deformation. I have the characteristic curve for the machine calibration. I have about 0.03 inches of deformation of the machine when we apply 32 TSF. 32 TSF, that translates to about 2,500 pounds. When you apply, that's the weight of a small car. Then this frame deforms 0.03 inches. And that's going to be taken out from the deformation of the soil when we put the soil. So this is done now. What I'm going to do is I'm going to remove the load, take the cell, put a sample, and we get it going. And if we have time, we can do the triaxial. Okay? All right. So we can stop that. So now what I'm going to do keep going now. Now that this is done, we have our machine deformation done. What I'm going to do, I'm going to close. I'll just close it. And I'm going to go to File, and I'm going to save it. Now, I save the file with this information now in it, and this is my new template. The template has the machine deformation already, and that's another reason when you run a test, you load this template. Right now, you only have one template. But once you start running tests, you can use a test as a template for the new test. Okay? So I'm closing here as I saved it. Okay, right now, just going to show you how we're going to set our consolidation sample. The sample is already trimmed in the ring. You follow the ASTM standard how you trim the sample in the ring. Basically, you have a chunk of the soil that comes out of the Shelby tube and disturbed soil. And use the ring as your cutting device. So you start from top like that, push it down, have like a plate so it's pushed uniformly, and trim the soil as you go down until the soil fills up the ring. And then once you're done with the trimming, you trim the ends, make sure everything is all trimmed nicely. And so you have a 2.8 for this particular case diameter sample by 1 inch. And the next step is to take the weight of the ring and the soil which you're going to enter in the software. Now you want to make sure that your porous stone is wet so it does not suck in the water from your soil. And you got your this is the filter paper, make sure also is wet, like your top porous stone. So you got your filter paper right there, and the porous stone. You got the centering ring. You hold it in place here. Make sure that everything is okay, it's centered. I'll put that one first. Tighten by hand, and Take your sample, put it, set it up here. Again, you don't have to be in touch because software will automatically make contact. Now what you need to do is have water ready, regular water, because the standard says the first minute of the test you add water. So we're going to be adding water. Again, the menu doesn't have to be in any particular menu here except for jog. So I'm going to go back to my software, and I'm going to load the consolidation software, load my template file, all the relevant information to this particular soil sample. Then the initial weight, specific gravity, any other information, water content, information about the water content initially. Now, I'm going to go over the specific of the software. Right now, I want to get this test going, so we'll have data tomorrow, but we'll have the projector, and we'll go over the software tomorrow and explain all these different things here. Is a standard sequence that I already have here in my template. I can change it now. I can change it during the test too, if I want to. I can change anything as long as I'm not in the step. While the test is running, I can change units. I can change anything I want. Everything is okay. The power on, switches are off. I'm ready to go. This is a test that typically, when you run it manually, the old-fashioned way, it would take you. What people do, use method A in the ASTM standard, and it takes 24 hours per load increment. And if you're doing 13, which we're doing here, 13 load increments, that means this test will take you 13 days to complete. And as a result, because it's so time consuming, a lot of labs I've been to, and I can show you pictures if you have time, you see 40, 50, 100 of these banks because they take so much time. But that's how they do it, I guess, the old-fashioned way. We use method B, which is the end of the primary, and these 13 steps, this test will be done tomorrow morning when we come in. Why? Well, first of all, this soil is not very plastic. I can see it here. It's got some fine sand, some silt in it, so it's going to consolidate pretty quickly. And second of it is not, I put my minimum duration as 30 minutes. I have 13. That's 6.5 hours. It should be done in about 6.5 hours. If somebody wants to come in the middle of the night with another sample, that's fine too. But if you work in a private sector on the weekends, people switch it over. So they come on the weekends and then make a switch over of the soil. So you got extra tests done between Saturday and Sunday.
For some reason, it takes more than 30 minutes to reach primary consolidation.
It will automatically, I put the maximum 24 hours.
Okay, so the machine's actually checking for primary consolidation.
Yes.
More than the time?
Yes. The deciding factor is the maximum duration for each step. And the maximum duration I put in is 24 hours. So no matter what, it won't go over 24 hours. But no matter what, it will stay for 30 minutes. Even if it takes 5 minutes to consolidate, it will still, and I can change that. If I see it is only taking a few minutes to consolidate, I can change my minimum duration. So what I'm going to do here, I'm going to do a run, start. Different name. Now, this is very, very important. this, and I will be mentioning it again and again and again. The test runs automatically. The data is automatically recorded. At the end of the test, you do not need to save the file. The data is already saved. People who have this equipment the first time, that's a very common mistake. At the end of the test, they say, I'm going to save it. And what they do, they overwrite it, and I got all that dreadful call. I lost my data. That's the only time you lost the data by overwriting it, because people are not sure what it's doing. So no need to save. If you need to save anything, do save as, because you're going to put the information of the water content, which is not available now after 24 hours, and you save it as. Those files are tiny. They are 26, 30 kilobyte. You can have 1 million tests here, and you're not going to clog up your hard drive. So save the original. Always keep the original the same. When you do any modification, save it as. So again, so it's going to make contact. The other thing is, you want to have a sequence or some kind of way of naming your files, so it will be easy to retrieve them. This is just making contact there. It's pretty much in contact. Now, this is my first stress on, and I'm going to add water. If this test is going to run for 2 weeks for whatever reason, you want to put some plastic wrap so it doesn't lose water, unless you're here to replenish the water. Now I go into view, test graph. So it applies the load. This is like your dead weight that you put in on the soil sample there. So it applies the load and is keeping track of the deformation of the soil. And it does also deconstruction here in real time to find the T100. So all this information is available here. Now I don't have to touch it. The test is going to run by itself from beginning till the end. So basically, in the middle of the night, it will be done. So when we come back in the morning, we'll have our data and the test. This video clip is going to talk about the end of the incremental consolidation. We had a test that ran overnight, and we put 13 steps. We're using method B, ASTM standard, where every step ends at the end of the primary consolidation. So the test is done, and I know that when we came this morning, there was a message on the screen saying test finish. I say okay. Now what you need to do to look at the results is to go to file. You cannot go to report. So there's one step before that. You go to file, and you're going to load or reload the same test that we run, and you open it. Now you have refreshed all the information on the screen. Then you go to report, graph, and you're going to see your time curves for the 13 steps. And you scroll through all these steps here. Make sure that everything is okay. 5, 4, 3, 2. This is summary curves. This is my plot of either displacement, vertical strain, or void ratio when we have the water content versus the vertical effective stress. By looking at the graph here, I can see that the test ran successfully, and now I'm ready to remove my sample from the frame so I can take the water content. There is a load that is still applied from the last load increment in the consolidation table. So to remove that load, we have two ways. I can do it through the computer there, or since I'm here, it's more convenient to do it through the keypad and the LCD. So I'll go on the menu here. It says 1, 2, 2 is position, so I go to position. And now I'm into a sub-menu that gives me the options of raising the platen, lowering the platen. And what I'll do, I do 2, lower, and enter. So now it's going to lower my platen. So I can release the load. I'll make sure that once the load is released, I just hit escape key to stop it. Now the load is released, sample is going to have a tendency to swell up. It's going to give me wrong water content at the end. So I'll make sure that I hold it together, and so that nothing will happen. So I got my sample here, and then I go to the sink and I dump the water. There's a sink over there. I'll just dump the water here. Oops. So the next step, what you do is you're going to take the sample apart by removing the loading pad, and then the centering ring, the top porous stone, and you get your sample here. You make sure you remove any excess water that is on the outside. So you dab lightly here, take all the water content, the extra water, and the first thing you're gonna do, you take the filter paper that was at the bottom, had stayed at the bottom, otherwise you'll have to remove it. You can see that the sample has consolidated, so it's below the rim of the ring. And now what you need to do is take this whole specimen in the ring and weight that. So you're going to record the weight, then take the soil out, put it in a moisture can, and take the water content, the final water content at the end of the test. And your test will be done. The next, in terms of water content and sample. Now, once you take the sample out, you need to clean up the ring and put very light coating of vacuum grease inside, so that minimizes the side friction of between the soil and the inner wall of the ring. So that will be done. And with the sample here, with the test result, you just print out the results, and you're not going to have the water content, the final one, but you can print the summary report in terms of vertical strain. So, and that's actually the recommended value. So you go into the report settings, and then you hit strain, you do apply, it will automatically change that the vertical axis here in strain. And then you go to view and print, and then you get a printout that will look like these here from the printer. This is a black and white, and you can print it in color. So you got all the information. You can print the graphs, you can print the tables, and you have several options how to report the data. And this applies to all the other tests, either direct shear or triaxial or permeability. So if you go into the report, and table and view next page, you have data here that is already processed. So what you can do, you can right click, select all, copy, and then you paste it into the spreadsheet. It's very simple. Or if you want to do your own data reduction, what you can do, you can go into view next page and you have all the data here and you can plot them again. There's also another option usually used for universities, which is dumping the data. So if you go into file dump, it will give you columns of time, load, and displacement. And from there, you can process your data on a spreadsheet. So you have several options available to you in terms of data and what you can do. Now, if there is a glitch in the data for whatever reason, something happened, there is an option here under report, edit, and you can edit the data, the raw data. You can delete a point or the sets of points. But what I do recommend, if you're going to edit the data, you always save the original data. So if you delete or edit anything, just save the file as a new file that is edited, because the original data needs to be kept intact. And that will conclude this video clip about the end of the consolidation test.